Okay, calculus summer review. We should talk about trig. And with trig, there's just so much that we can talk about. On our review packet, which really is on page 12, where we have quite a few problems, I'd like to look on that page, but really just refer back to the unit circle. A unit circle is a circle with a radius of 1 centered at the origin. We would, of course, have the following ordered pairs at the axes. 1, 0, 0, 1 at the top, negative 1, 0 down below here is 0, negative 1. In radian measurements, this would be 0 radians, pi over 2 radians going counterclockwise. Coming down to this negative x-axis, we'd be at pi. Down below here, we'd be at 3 pi over 2. And of course, what I want you to know about the unit circle is that really on the unit circle, the x-coordinate will represent the cosine of an angle, and the y-coordinate would represent the sine of that angle. And it goes alphabetically. Normally we have x comma y. X goes before y in the alphabet. C goes before S in the alphabet as well. So, for example, just looking at this picture up here, if someone were to say, hey, I wonder what the cosine of pi over 2 is, the cosine of pi over 2, of course, would be 0. Similarly, the sine of pi over 2. Pi over 2 is way up here at the top. That's the y-coordinate. You could see it would equal 1. And that's just the very basics, but I think what most kids could find to be a little confusing about this is telling the difference between what's occurring at pi over 6 and also at pi over 3. And that would be equivalent to 30 degrees and also at 60 degrees with pi over 3. Something I want you to remember is that 1/2 is equal to 0.5. Radical 3 over 2 is about 0.866. And, radical 3 over 2 then is bigger than 1/2. Why am I bringing this up? Well, I just wanted to speak to you about maybe looking at things a little bit differently in terms of having a quick visual approach to evaluating some trig functions. Say, for example, you were looking at pi over 6. Pi over 6, we'd be interested in finding what x and y coordinates are here at the unit circle. But dare I say, what you could do is draw yourself a right triangle. Now, what I want to point out to you is that there is an x distance on the triangle. That's what I'm going over right now. And then a y distance as well, a horizontal and a vertical component. Notice that the horizontal side is a lot bigger. It's larger. You can visually see that. And that means that the x value would have to be radical 3 over 2. The y value, of course, would be 1/2. And this can then help you out, knowing then that, say, the cosine of pi over 6. Well, cosine is always the x-coordinate. It's root 3 over 2. What about the sine of pi over 6? Well, from this visual approach, you'd say, well, it's the y-coordinate. It would have to be 1/2. It's that short leg on that right triangle. In a similar way, we could take a look at what's happening at pi over 3. Now, at pi over 3, we could draw in, of course, another very similar situation. We could say, let's draw in our right triangle here. Look, we've got a horizontal leg and a vertical leg. It's this vertical leg now that's big, and the short leg is the x distance. So the x would have to be 1/2. The y, you can see this vertical distance is a lot bigger. That's your root 3 over 2. So what you could then say is the sine of pi over 3. Well, it's got to be the y-coordinate at pi over 3. That's root 3 over 2. What about the cosine? Well, the cosine of pi over 3 is going to have to be a half. And usually at the pi over 4s, kids feel pretty good. They'll know that sine and cosine have to be root 2 over 2 for both of them. But this is a way to get you some help when you're working with angles at pi over 3 or pi over 6. You could actually make a real quick diagram, not having to recreate the entire unit circle, mind you, just a little bit, and ask yourself, hey, what's the larger leg? Is it the x leg or the y leg that's bigger or smaller? And at pi over 6 and pi over 3, you'll always have values of 1 half or root 3 over 2 for sine and cosine. So just a little bit of some help for you there. I'd like to actually get in and solve some equations as well. Let's solve over the interval between 0 and 2 pi. So we're going to be in radians, very much like our review worksheet. And this is on page 12, some problems that are kind of similar. None of these are actual problems, but they're pretty close. Let's say I gave you sine squared of x equals the sine of x. You could say, well, could I solve that between the interval of 0 and 2 pi, including 0, not including 2 pi? What I strongly suggest that you do is first get 0 on one side. Add or subtract whatever other terms you have, and then factor. There is a greatest common factor. There is a sign that I could pull out for both. And what would happen, just factoring this out, you'd have sine of x times sine of x minus 1. Now, using the zero product property, also known as the zero factor theorem, I'm going to take both of these parentheses, or both of these factors, I should say, and set them equal to 0. And solving here, I will just get sine of x is equal to 1. Well, we're asked where sine could be 0 and where sine could be 1. Let's go back to the unit circle real quickly and remember that we'd have 1 comma 0 over here, we'd have 0 comma 1 over here, negative 1 comma 0, and 0 comma negative 1. Now, sine is always the y coordinates. You could say where on the unit circle, going from 0 to pi over 2 to pi to 3 pi over 2, and then even coming back here to 2 pi, we won't include 2 pi. You could say, where is sine equal to 0? Well, the y values are 0 only on the x-axis. You could see that you could have x equals 0, you could have x is equal to pi, x equals 2 pi. Sometimes kids want to include that also, but the boundary is not included, so we won't need that. So where are those y coordinates on the unit circle going to equal 0? Well, only at 0 and pi. How about sine of x equaling 1? Where is the y value going to equal 1? Well, at the very top, at x equals pi over 2. So what's our solution? Well, three answers. X equals 0, x equals pi over 2. Okay, so let's do another problem and see how this is coming. Maybe we could take a look at maybe something with cosine in it instead. For example, 2, let's say that we had 4 cosine squared of x equals 1. And again, my advice is first subtract a 1, get 0 on one side, and then let's try to factor that. This is a difference of squares. We'd actually get 2 cosine of x plus 1, 2 cosine of x minus 1. And using that zero factor theorem, I'm going to set both of these parentheses equal to 0. Zero factor theorem, as many authors call it. Here we'd subtract a 1 and then divide by 2. So cosine of x could equal negative 1 half. over here, if we add a 1, real quickly, we could see that cosine of x would equal positive 1/2. Something of interest, you're going to notice that cosine could be positive or negative 1/2. We're going to be interested in all 4 quadrants. And you might remember that 1/2 is actually going to be smaller than root 3 over 2. Let's just worry about the first quadrant. This is where cosine could be 1/2. Cosine, remember, is the x-coordinate. So as we're looking at this, cosine of theta and sine of theta, you might wonder, would we be at the pi over 3 or would we be at pi over 6? Well, you might even need to real quickly draw that in. If you drew in a triangle at pi over 6, you could see that the x length is way bigger than the y. And that would pertain to x being radical 3 over 2 then. Because the larger leg in a 30, 60, 90 right triangle in this circle would be root 3 over 2. Instead, we're going to have to come over this way. And we're going to know that that's going to be at pi over 3. Now, something to help you out. I hope you remember all students take calculus. You're saying where trig functions are positive. All trig functions are positive in the first quadrant. Only sine is positive in the second quadrant. Tangent is the only positive trig function in the third quadrant, and cosine is the positive trig function in the fourth. So we're looking, if we're solving this cosine of x equals 1/2, obviously we found that we're at pi over 3, but you would also like to know what's down here. Hopefully you're very familiar with the unit circle and you'd know that down here would have to be 5 pi over 3. Another way to think of it, here's 2 pi. If I am pi over 3 smaller, you'd take 2 pi minus pi over 3 and you'd be at 5 pi over 3. In these other quadrants, this would be where cosine would be negative. So this would be solving cosine could equal negative 1/2. You could see that you'd be pi over 3 short of 1 pi, which by the way is 3/3 pi. If you're pi over 3 smaller than that, you'd be at 2/3 pi. And if you went a little bit beyond that, you'd be at 4/3 pi. So where would cosine have to be negative? Well, at 2/3 pi and 4/3 pi. So just jotting those down. Hopefully you can see then that there are 4 distinct answers. Answering the question then, we could say, well, where exactly are those solutions? Well, we could say x would be pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Okay, real quickly, let's take a look at maybe one last one, at least setting it up. Just want to take a peek at something that might involve more factoring. Here's example 3. Sine squared x plus 2 sine x equals 3. Tell you what, let's subtract the 3 from both sides and then factor it. Hopefully you remember that you can factor a trinomial even like so. Here's sine of x, sine of x. Let's make a plus 3 and a minus 1. That's how this would in fact factor out. Set both of these equal to 0. And you very quickly would solve the second equation to get sine of x would equal 1. Where on the unit circle would the y value be 1? Only at pi over 2. We saw that from example number 1. That's the only place where you have a y-coordinate of 1. The second problem, you're saying sine of x equals negative 3. You know what? The smallest your y value could ever get is negative 1. There's no solution for this. We're not going to worry about that. Only one answer we're going to get. and that's at pi over 2.